To illustrate this process, we're going to construct a molecular orbital diagram for carbon dioxide. So the first thing we need to do is we need to determine the Lewis dot structure for CO2 and also have an idea of its geometry. So this has already been done. So carbon dioxide, of course, is a linear molecule with carbon as the central atom and the oxygen atoms as the outer atoms. So now we're going to assess it for different symmetry operators that are inherent within the molecule. The first one we're going to look for are rotational axes. So rotational axes are axes on which the molecule can be rotated without changing the nature of the molecule. Okay? And so for instance, we can draw an axis down, an internuclear axis down the center of the nuclei of the oxygen, carbon, and oxygen atom, and we can think about rotating the carbon dioxide along this axis. And so what we end up with is no matter what angle we rotate the axis, the carbon dioxide remains the same. So the carbon remains in place, the oxygen and the two oxygen atoms remain in place, right? And so this is, in this case, right, because it doesn't matter what angle we rotate this, right, this is called a C infinite axis. So that's a rotational axis of infinite degrees, right? Now, by contrast, right, we have another rotational axis that goes through the center of the carbon, and we can think about rotating the axis from the top of the carbon, where if we rotate it, the oxygen atom on the left-hand side rotates the position of the oxygen atom on the right-hand side and vice versa. In the end, right, the carbon dioxide is still, there's an oxygen atom still in the place where there was an oxygen atom before, and of course the carbon has not moved at all. So we retain our symmetry of the molecule on this, and we have a C2 axis, okay? Now there are infinite of these because we can put the C2 axis within the plane of the board like we have drawn. We can put it perpendicular to the board or anything in between, and we're going to still exhibit the same symmetry. Okay, so we have an infinite number of these C2 axes, okay? So the next one we're going to look at, so these are called rotational axes. Okay. But we can also think of what are called mirror planes. And so what this is if we put a mirror, for instance, in the center of the molecule, okay, then we have a, then what we see if, for instance, we split this carbon dioxide and the atoms in half and we put a mirror plane in its place, what we would see is that on both sides of the mirror, they would be identical. Okay, so this is referred to as a mirror plane, okay, and we refer to it as sigma, okay. There's also a mirror plane perpendicular to this one that goes through the center of the carbon atom and splits the two CO bonds on either side of the mirror. Okay, so we have another one there, and then we have another one that is perpendicular to this as well. Okay, and so if we think of this in relationship to the highest order rotational axis, which is our C infinity, right? What we see is one of these mirror planes includes the internuclear axis. So we refer to this as sigma v. So it's a vertical mirror plane. Versus the other one is horizontal to this internuclear axis. And so it's perpendicular, and we refer to that as a horizontal mirror plane. Okay, so strictly speaking, right, again, there's one, similar to our rotational axes, we have one horizontal mirror plane, but we have an infinite number of vertical mirror planes because we can place this, this mirror plane either within the plane of the mirror of the light board or perpendicular to the light board or anywhere in between, and we'd still have that mirror symmetry for the molecule. Finally, for the purpose of this, right, we have what's called, let me back up. So these are referred to as mirror planes. Right. Finally, for the purpose of this, we have what's called an inversion center, where if we go through the center of mass of the molecule, which is in this case the nucleus of the carbon of CO2, if we start from the oxygen atom, and we travel through the center of mass to an equidistant location on the other side of the center of the mass, we should, if we have inversion symmetry, then we should see the exact same atom. And in fact, we do. We see oxygen, okay? And if that's true for all the atoms within the molecule, where if you travel through the center of mass an equidistant amount from where you started, and you see that it's the same atom, you're going to have what's called an inversion center. So in this case, right, we have an inversion center for carbon dioxide.